Hello everyone. Please send something in the chat if you can hear me. I'm trying to test the audio and yeah, let's hope it works. Not sure about the audio quality or volume, so turn it up or down. Amazing. Yep. So I'm not going to teach C++ from the ground up. It's probably like a really hard and time-consuming task. We don't have 2 weeks full time. Yeah, but we will start with some basics. I think we will start functional programming in C++ from the ground up. Yeah. Let me do something with the background noise. Yeah, there's like some noise outside the window. Let's hope I won't suffocate. Anyway, shouldn't take long. We will just start slowly. So Twitch shows me I have some viewers, and it's actually more than I expected, especially for the first stream. So we can start. As for resources, actually, if anyone can suggest any resources, feel free to drop them in the chat. I'm going to walk through one particular resource today, and maybe we will see some more. But for today, my plan, and I guess for a couple upcoming sessions and Twitch streams, is that I kind of want to see the capabilities of functional programming in C++, and like how feasible it is, how convenient, how ergonomic. I already expect it won't be like the same as in like functional programming languages like Haskell and OCaml, but still, let's see how far we can push it. So actually, let's just start. I think I have everything ready. You should now see my screen. Ideally, the Google Chrome browser and maybe the chat, and it's still me, hopefully. Yeah. Expect some technical difficulties for the first time, but hopefully should work. So just to give some story and like some background. So I actually tried to learn Haskell several times in my life, and I failed. But then I found like this course online, like SYS 194 Introduction to Haskell, and it actually changed everything for me because it somehow clicked for me. I was able to understand Haskell, do the stuff, and specifically functional programming, how you think with these concepts of higher order functions and all of this stuff. So my plan for this series is to actually walk through this course, but do it in C++. So we are not going to learn Haskell, and that's why I'm going to skip all of these tutorial sessions. It is a great course, and if you do want to eventually like learn Haskell, I highly recommend it. Like, it worked for me, it worked for how I think about programming, how I think about studying, so maybe it will work for you as well. But we are going to do some homeworks in this like from this course, and we will see how far it goes. So let's start from the beginning. Let's start from the homework 1, and we'll do it actually in C++, so not in Haskell. I maybe occasionally compare C++ to some other languages, maybe to see how they work, but we're going to do them in C++. Okay, let me make it a little bit bigger so everyone can see. Okay, so let's start from the beginning. When solving the homeworks, try to create not just code that works, but code that is stylish and concise. So here, kinda like when I was learning Haskell 10 years ago, I probably just skipped all of this introduction section, but you can see that the values and the goals are kind of set from the start. So the idea is like to solve, but also not really about performance or like I don't know, like using some design patterns. The idea is to write code that is stylish and concise. So like it's really about being as terse as possible, and functional programming is generally about this. So we are not going to do this in C++. It's probably going to be more verbose than in functional programming languages. But generally speaking, like functional programming encourages composability, and it's like not a silver bullet. You don't get automatically elegant, beautiful code, which is also fast and performant. There are some trade-offs. There are some techniques to make it faster, and hopefully we will look into them. But we will just try to see what's available out there and how to solve the problems. This is a style guide on the website for some general guidelines. Okay, we are going to ignore it. Try to write small functions which perform just a single task, and then combine the smaller pieces to create more complex functions. Don't repeat yourself. Write one function for each logical task and reuse function as necessary. So dry is a kind of like controversial pattern. You know, I think I made like several tweets about dry. Great source of engagement, by the way. But the idea is that you don't repeat yourself exactly. So like if you have exactly the same functions, why would you write it twice? You can just reuse it. The problem starts is when the functions are not really the same, and then you kind of try to do abstraction, and it's more difficult. And in functional programming languages, the idea is that this like composability is really the key. So you have this like really small blocks, almost like Lego blocks, and you build from them, because like Lego blocks are composable and reusable. You just have one, okay, you duplicate them multiple times, and you can build anything from them. The same with functions. You have a lots of simple and small functions, and you build gigantic structures from these functions. So we will try to not repeat ourselves, but generally there is like a trade-off. Be sure to write functions with exactly the specified name and type signature for each exercise to help us test your code. You may create additional helper functions with whatever names and type signatures you wish. Okay, we will try to do. So validating credit card numbers. So the first homework is kind of implementing this standard number card validation algorithm. Have you ever wondered how websites validate your credit card number when you shop online? They don't check a massive database of numbers, and they don't use magic. In fact, most credit providers rely on a checksum formula for distinguishing valid numbers from random collection of digits or typing mistakes. So this is not entirely true. I mean, quick checksum of digits is like really quick check of like basically making sure there are no typos. But then like after this sent, the card actually is sent to the actual provider like Visa or MasterCard, and then the database checks like with the account number or whatever, or like your CVV code and expiry matches. But basically like there is a quick check, like when you type an email address, you can at least write on your front end simple like functions that checks whether the @ sign is inside the email. So at least like you won't spam your API whatever with lots of stuff. But yeah, checksum does, and we are going to implement this checksum. And yeah, in this section we implement validation algorithm for credit cards. It follows these steps. I think, I'm not sure if it's mentioned below. Well, actually this like algorithm, like finding the checksum of card numbers, actually called the Luhn algorithm. that in the chat, like if you wanna find it later. It's like the standard algorithm how you verify that card numbers are actually there. And yeah, we are going to actually implement Luhn algorithm in C++. Question: C++ is trying to be like Rust. Why I need the C++? I think C and Rust better than C++. So there is a ton of code in the world, like in real world, in like banks, financial companies, trading funds, like game studios, video game, I mean, some controllers. There is already huge code bases written in C++, and people still have to maintain them. You cannot rewrite like hundreds of millions code of C++ in like other language or whatever, even with AI, easily. So they still have this code and they still need to maintain it. And it would be nice if they're like, you can still leverage new features. And Rust has lots of like nice compile time guarantees to prevent you from doing stupid things. C++ requires more discipline, but there is still appetite to like improve the quality of code, and those C++ adds more features. But yeah, realistically, you just cannot rewrite all C++ code to another language. I feel like it's never will happen. Like the complexity of this is too much. But yeah, hope that answers these questions. Anyway, back to the algorithm. So the algorithm is the following. Double the value of every second digit beginning from the right, that is the last digit is unchanged, the second to last digit is doubled, the third to last digit is unchanged, and so on. For example, 1, 2, 3, 8, 6 becomes 2, 3, 16, 6. So basically we start from the right. The last one is not changed, this one is doubled, so it becomes 16. 3 is not changed, this one doubled becomes 2. So basically this is the first step, we have digits. So add the digits of the doubled values and the undoubled digits from the original number. For example, 2, 3, 16, 6 becomes 2, 3, 1 plus 6, 18. So the idea is that we now need to find the sum of all digits here, but after we doubling some numbers, like if the number is bigger than 5, then it will become like a double digit number from like 10 to 18. And like we also need to find the sum of digits of this number first. So we don't just add numbers. If we add them, it will be like 5 plus 6, 11 plus 16 will be 27. We also first find the sum of digits of these numbers. So yeah. And the last step is that we calculate the remainder of the sum. And if it's divided by 10, basically the last digit is 0 eventually, then it's like the number is valid. And in this case, like the sum is 18, so it's not divisible by 10, which means this particular number, whatever we started 1386, is not a valid credit number. And the exercise kind of guides you, like in Haskell, how to implement this algorithm in Haskell. So you have this like functions, 2 digits, you convert number to digits, you like have 2 digits reverse, which like does them in the reverse order, and there are like double every other, and you see like really small functions. Then we like finding sum of digits, how to do all of this stuff, and then we do validate, which is basically do the stuff. And there are some test cases here, which is actually really nice. So we are going to do this in C++. We are going to use functional programming, kind of like in a similar style. But first, before we do it in a like functional style, let's try to solve like this problem somehow, like in really vanilla, simple C++, just to have like something as a baseline and something to test again. So I think I'm going to switch to VS Code. I've been using VS Code for my programming, both at work and at home. It works well for me, so I don't really like use a lot. For me, it's fine just to type code and to learn it, and it works great. So we are going to start like from the very scratch. I already created a directory sys 194 Haskell in C++. This is like directory. Ignore this file. Let's delete it and let's try it completely from scratch. So there are like 12 homeworks in this course. Let's be ambitious and try to solve all of them. So let's start with homework 1. I use like CMake and Make to build C++ projects. I mean, maybe not ideal. If you actually have any suggestions, feel free to let me know afterwards. But the way I do it is that I just create CMake list txt. Okay, whatever. Okay, I already have GCC. Does some configuration. Hopefully we'll even get like go to definition and some inline hints. I actually already have like a minimal CMake list, so let me just copy it here. Don't really remember the full syntax. It just gets that it just does the job. So whatever the version, let's call it, I guess, homework 1 project. We are going to use the latest available standard. So my GCC version, I think it doesn't support everything from this standard, and so no print line. We're still going to use cout to print stuff. But anyway, let's start with something. Come on. Okay, it does nothing. Let's actually write like hello world just to make sure that we can compile and write stuff and run stuff. Okay, I also already have this like make file, which just not here. It just runs CMake and creates the project. So if we just run, if we go here inside homework 1, here we have make file. Let's do make build. Oh my god, is this going to be like this? CMake is going to be really stupid. Yeah. Okay, so it built some stuff. It's inside the build directory, and we see that our homework executable. So this is like what is specified here in the executable homework 1, and we can actually run it. So if I go inside build, let me clear it. If I go inside build, homework 1, prints hello world. So it works. So we're actually going to recompile code a lot. So let's actually do this command that it like that actually rebuilds, recompiles, and runs our project in one go. And because there is some noise output from CMake, I'm just going to say this, just some delimiter. Okay, this should be our start. How come your CMD is colorful? So this is actually what I use. I use Starship. This is like tool written by Rust. It has a lot of stuff, and it provides this config. So my config is in. Let me make it just a little bit bigger. Store config in like home.config/starship.toml, and my config, it's actually on my GitHub in the .files repository. It has this like the stuff with colors and configures different languages like Haskell, OCaml, and C++, and Starship kind of automatically figures out what language are you using right now. It does it in a really dumb way. It just checks the files that you have and extensions that you have. So in my case, if it sees any files with .cpp or .h or .hpp extensions, or if it sees a CMake list file, it will assume it's C++, and it will print this like prompt saying what version of C++ I'm using. And there are like some hack nerd font things just to make it less boring. Anyway, Yeah, you can find it, my Starship config on GitHub. I can actually send the link. 1 sec. Oh my god. Yeah. Yeah, speaking about return 0, actually in C++ you don't have to write return 0 in int main function. It's kind of like a nice feature. I don't know when they added it. I remember when I was learning C++, it was kind of expected, but now you don't. If it's main, it implicitly added like return 0, so it's slightly reduces the noise. I mean, it's just one line across your entire project, but imagine how many mains in the world out there in C++. It probably saves like 1 million lines of code total in the world, so it's nice. Anyway, let's write the Luhn algorithm, and let's actually write it in the standard imperative way. How would you do it, like in the vanilla C++, vanilla imperative, like any actually language for whatever it matters? So it's like it's a language validate. So it's a function validate, and it returns a boolean. So whether like the number is valid or not. Let's call it validate 1. Like it's the first implementation. It takes a number. So let's take long card number, and we will return. So the number is like 16 digits, and long I think it's 9 by 10 to power 18, so it's like 18 digits. So I think the card number should fit inside long, which is nice. And there already were some test cases in the course, so we can actually write some tests already. Use test-driven development, and it's best. I'm not going to use any fancy testing frameworks. I'm just going to use asserts. And basically what we're going to do is that we're going to use assert. I'm going to say validate this number, and validate 1, and validate 2nd, and so wait, the first one was true, so we actually expect here no. Okay. Yeah, very simple implementation. Obviously wrong. TFC run like it's aborted. Assertion this validate fail. So this actually should not be validated, but now our implementation also returns true, obviously, and nothing happens, but at least the code compiles, and we have some tests, and we have some blueprint we can start from and do. So how would we do it? So we need to kind of like find all the digits, and we need to double every second digit, and we need to find the sum of all digits and basically check if it's divisible by 10. So it's a really simple algorithm. I don't know, if it were like LeetCode, it would be like LeetCode easy, probably just a really simple 5 or 10 minute coding challenge. Let's try to do it in kind of how we would expect in C++ and C. It's like with 0 allocations, as much as possible, like to do in place and try to do really efficient. So what we are going to do, we are going to have like sum of all the digits. So our number is like big, long, but digits, they are really small. They would fit even probably like in short or maybe even byte or whatever. We are going to do some arithmetics, and actually I'm not sure if C++ optimizes casts from different numbers to others, but anyway, let's see. We have our sum is just 0, and while our card number is bigger than 0, what we are going to do, we're going to kind of cut the last digit from our number. If it's even, like if it's like every second digit, then we are going to double it, and we are going to add result to the sum. So sum will be like sum of our digits, and we are going just to check if it's divisible by 10. So the logic is happening here. So again, let's do digits, which is like card number. This is like the last digit, and we are going to cut it, which is like we will divide it by 10. Now we want to check if it's like every second digit. So we can kind of have like counter, which like goes 1, 2, 3, 4, 5, and it checks whether the counter is even. But because we know it's like even odd every second, we can just have like a bool, and we will kind of how do you say it? we would flip it every cycle iteration. So we will say if is even, so we are like on even digit we will do one thing, otherwise it's not even, we just add the digit to the result, and we will flip is even. So if it is even, we need to multiply digit by 2, and now if it's actually like if it's like bigger than 10, if it has like multiple digits, more than one digit, we need to also find digits of this digit first. So there are multiple ways you can do it. You can check, let's say, if the digit is bigger than 10, and you can do kind of the same thing, like while it's bigger than 0, let's cut, let's add it to sum. We can introduce this loop. I'm going to be lazy. I'm going to kind of make an assumption that this is like digit. It will never be bigger than 20 and bigger than bigger than 20. Therefore, there will be maximum 2 digits, and I can actually do like some arithmetic and say so it's like just with 2 digits, and one of the digits is that digit mod 10, and the second digit is just a digit divided by 10. So this works even for single numbers, because let's say we have digit was 4 multiplied by 2, now it's 8. We will get modulo 10, it will be 8. We divide by 10, it will be 0. So basically we just do digit 1. Oh my god. My Vim failed me again. One more time. Let people process this one more time. Sum plus digit 1 plus digit 2. So this is basically how we would calculate it. Just 2 digits, like a special case, and there's like no heap allocations here. We just do modifications in place and do the stuff, and let's actually see if it works and expect it. So it did not actually work for our first number. It did not validate it. Well, this is where the fun part starts. Like now we will have to debug our implementation, and this is kind of like can be like kind of like a lesson in some sense, that we wrote some implementation, it does some smart stuff. It might not be really obvious what's happening here. Maybe like you can sit for 5 minutes. I'm more of a contemplator, and like sitting for 5 minutes might actually work. But we can actually do something more productive and try to debug this stuff. This happens, and the idea is that like this just does some modification in place. It's not really like really introspectable. What you can do, is you run a debugger, and I guess actually never run debugger on my home machine, so let's see how it works. Okay, so it works surprisingly better than I expected. Okay, our sum is 0, our number was expected to be true, right? Interesting. Anyway, oh my god. Sorry, we don't need to debug our origin of the error. We need to check that it equals 0. So yeah, one of the reasons I'm not really a big fan in C++ is that there are lots of implicit casts, and we say we return integer, but I actually like mod by 10 is a number, and number is implicitly converted to boolean, and it works this way. Like if the number is 0, it false, otherwise it's true. So when we did modulus by 10, it was like the opposite what we want. So we actually want true when it's 0. Let's try to do this again. Okay, this. I'm lost. Anyway. Yeah, now it works. The tests are passing, and we see that our implementation is correct. We can do more tests. Feel free to drop your credit card numbers in the chat. If you want to test, we can run them through this algorithm and see if it works. Definitely nothing sus is going on here, but we can trust the test from the course, whatever it works. And just to pause, like why this implementation might not be good, why we even need to reach to like functional programming or whatever. So this like function is really small, so you can write it once, you can implement it, you can do like code review, you can write tests, you can write documentation, what's happening. You may even like read it once and understand. If you do it like maybe read in 6 months, you won't be able to easily understand it. So you need to again to deep dive. Again, because it's a simple function, it's not really as hard. Like no hard math is happening here. There are like more fundamental problems. Like what are we doing here? We want to find digits of a number. So it's maybe not like really often in your life you want to have digits of a number, but it does sound like a common task a programmer might want to do once in a while. I don't know, card numbers is one. Maybe you know you display something on the form and you want to know how big is the number and you want to calculate how many digits it has. Actually, there is like this really fun thing I discovered while I was preparing. Let me show you in the browser. This is a beginner-friendly class. What we wrote here in the like validate function, this is the most beginner-friendly C++ you can get. So you do cout to print stuff, and you do just basic simple function like no numbers, no test stuff. We are going to increase difficulty really soon in 5 minutes, but for now this is pretty vanilla. But anyway, what I was wanted, how many digits in a number, C++. Yeah, so I found this link, like how you can quickly calculate how many digits in a number, and there's like this really fun function, which I mean, you kind of understand what it does. It just checks with every number, but it does like in a binary search way. So it first compares like with, I don't know how many digits, maybe probably 9 zeros, and it kind of looks like a binary tree, so to simulate binary search. And at most you have like what, maybe five ifs here to actually calculate how many digits you have. Like you can write just a single while loop, like in the example, so it will divide by 10 and calculate number of digits. All this like clever hard-coded trick. So you can write all of this really smart code that does one job, and does it like really well and efficient way. But then the problem is that kind of it does one job and it's not always reusable. So this is the problem. Like we haven't built this function from like small reusable primitives. So the primitives here are really small. It's like language constructs, like if else, plus, multiplication, division, while loop, so like variable declaration. And we have this one single monolithic function, which is like just sits there. And let's say we cannot easily extract function like get me digits of a number. Like it's somewhere here implicitly, like it's not explicit. And we kind of want, like even in this function, we want to have like function give me digits of a number twice, like first when we calculate the digits of card number itself, and second when we multiply by 2, we also kind of want more digits. So here I just made a quick shortcut, but here we actually also want to have digits and iterate for digits, so it's not really reusable. And then we do this stuff, and when we have all of these monolithic functions, we implement them from scratch again and again. It becomes really tedious, not productive. Nowadays we have AI that can generate a lot of this code for you, so it kind of mitigated all of these problems. But now there is a second problem. Like now you have all of this like massively generated functions, and they do this the same thing again and again, and you want to change one thing, but now you need to change all of the functions, and you rely on agents to do this stuff, so it becomes quite tiresome. So functional programming takes the opposite approach. It's kind of like in some sense like Unix philosophy, like do one job and do it well, and then compose it. So we have these pipes, we send data from input to output, and we process and all of this stuff. And that it might not always be efficient, but it's good enough, and especially in C++, because it does lots of optimizations for you. Smart people created standard library, and it does lots of optimizations under the hood. You get this not decent enough performance. And if you see that it's not really fast, let's say you're developing a video game, and there you really need to squeeze every bit of seconds, and you might optimize like one particular function. But overall, the idea is that you build the small Lego blocks, and then you compose from them. So the code might look a bit scary, especially if you haven't seen it before, done this stuff, but let's actually see how it can be implemented in a functional way. So the idea is that we have these pipelines, and we feed data from one to another. So if you never worked in a functional programming way, it might be hard to kind of think in this way. How do you transform this like really monolithic, like atomic, like while loop, it's like unbreakable, into pipelines of stuff? So it does require some experience, but the overall sentiment here is that we have pipeline, and actually in the course, like in the Haskell course, like PDF, all of the steps are kind of given to you to kind of teach you this pipeline way of thinking. But we have like this pipeline that we convert a number to digits. No, so we were given a number, and we have like some digits. Then we digits to double digits, so we doubled every second digits. So we then like have this digit, and we double every second digit, well, from the end, but in our case it will be simpler. Then we transform double digits to sum of digits. Actually, we map so double digits to single digits. So we need to kind of go through digits and see if it's a big digit, we convert to like single, we find its sum, and then single digits to sum of all digits. So this is kind of like 4 steps. Hey everyone. And we are going just to do exactly that. We are going to write a different version of function validate, and we are going to see. And the idea is that we are hopefully trying to reuse this like digits when we want to convert number to digits. So here we have digits, and here we have digits, and we want to reuse functions. So it's not always about like performance again, but more how we can be more productive and do this stuff. So let's do different version of function validate. Let's call it validate 2, and we are going to have the same test cases for validate 2. So we want to convert numbers to digits, and function programming focuses on creating this like small reusable functions. So how can we convert a number to digits? Like we need to return like some digits. So if we want to be like truly functional, and if you want to like follow idiomatic modern C++, we kind of want to create a lazy generator, like lazy sequence, lazy view that lazily produces digit by digits and you consume it. This is definitely going to be more advanced than some people expect, but for now let's just return vector. Not the best solution because it does have some allocation, hopefully not too much, because our like card number is not big, so it's still manageable, especially if you run it, let's say, on a front end, let's say on a client or whatever. Usually every client has their own machine, so you're not overloading your system, and it's not a big deal. But we're going to return like a vector of digits, actually int, and we're going to call our function digit. So we have just one function that does only one thing, it turns us digits. To use vector, we need to include vector. By the way, I forgot to ask if you can see the code all right, but just in case, let me increase the zoom a little bit. I'm going to publish all the code to GitHub anyway, so you can have a look at it later. I'm planning to upload this video to YouTube as well. You can always rewatch it if you skip some sections. I appreciate that you're joining right now and kind of like watching it online, for providing some interesting comments. Anyway, everything will be accessible later, don't worry. Okay, so let's create this vector of digits. We're actually going to do exactly what we did here. I'm just going to copy it to simplify our stuff. So digit is like, well, numbers bigger than 0. We divide it by 10, and we kind of need to create a result where we are going to push all our digits. Okay, let's call it just result. Our vector, and we just push back. So we kind of extracted this one particular part into several functions. We take a number, like a long big number. We create like a result vector, and while our number is bigger than 0, we extract last digit and we push it back to our result and we return it. So we just solved one problem and we focus just on this problem. So a few notes. So vector kind of allocates memory on a heap, and it's like it's a dynamic array. It will expand like size 1. I know what's default, maybe it's actually 10 default, then double, and so on. So for big numbers it will take like multiple allocations, like a dynamic array does. You can reserve space in advance. You can use like that function I just showed from Stack Overflow, how to determine how many digits in the number, and you can just reserve that many space if you really want. But if you really, like if you write like a library function to be specific, but here doesn't really matter much, we can go with simpler solution. There is only one problem with this function, is that it doesn't work for number 0. Like if the number n is like 0, then this loop doesn't work, and we just return empty digits. Ideally, we want to do something with that. Ideally, like we can do something like that. So we are not going to bother with like patching our loop. I think it's possible, like you can do while true loop, do some break in the beginning. It will be really ugly, but we can just do this stuff, like here using like uniform initialization from C++, we can just create vector of one element, and we can actually test this function. So first of all, let me comment this, and in digits of 1, 2, 3, 4. Digit. Let's just see if it works. Before we jump and implement all of this stuff, it's actually helpful to kind of do stuff gradually one by one. Okay, I need to return something here just to avoid boring. So here you can see that we return digits in the reverse order already, and normally, I know for the library function, you might actually want them to return in the proper order, like from most significant digit to the less significant digit. But in our case, it's actually better to return in the reverse because we want to double every like second digit. So we did that, like we extracted a function digits, we extracted like this problem solve into reusable function, and it might not be like as efficient as doing like in place, but the idea is that now this problem kind of solved. Like if you wanna ever find the digits of number, you just call this function. You don't need to implement it, you do this stuff. Again, it's not a really big function, but this stuff accumulates. Like you need to solve one problem, then another, then again and again, and you're solving the same problems again and again. And it's nice that you own the code, that you understand it, but at some point it's too much. You kind of want to be productive. So at least this problem solved, we can reuse. Yeah, don't worry about this notation. So what we want to do next? So we kind of now want to double every second digit. So if we were to do this in like imperative style, we would iterate through every like second digit from the start and like multiplied by 2. So what I'm saying is that for index, okay, let's do like proper index starting from 1, so elements of vector start from 0, so 0 is like first, we need to double every second, so starting from 1, while I is okay, let's actually do card digits is digits of card number. You need to create digits, and then card digit size plus plus, not actually plus plus, we want to double every second, and just going to do card digits of I multiplied by 2. So this is how you can do this. Again, this is a simple code. It works. Like you have to pay attention to indices, that this stuff is properly works. We are going to do this in functional style just for fun. And for that we are going to use ranges in C++20 and some stuff introduced late in C++23. So ranges is like this huge library of functional stuff. Let me actually show you. This is like introduced in C++20, like ranges library, and it allows you to iterate through different stuff. And you can see that there is lots of stuff here. There is like ranges and views, so like different concepts. And the idea is that kind of view is not owning like view of some sequence, and it's like lazy iteration. So with views you actually can do like lazy iterations, and there are different functions that you actually would use in a functional programming language, like drop while, take while, reverse, all of this stuff. And what's interesting is that there are some examples at the end. Let's say you have some collections of like array of integers, and you have some lambdas, and you can see for this array I pipe it to views of filter, so I filter only all even numbers. You can see this lambda is just checks if number is even, and then I transform all of the numbers to square, so I like multiply number by itself, and I print the number, and you see squares of even numbers in the list. So it's kind of like the functional style of doing these things. And the internals of this library, I would say kind of a little bit hardcore, a little bit maybe complicated for something, especially if you're just beginning. They make sense, it's just how it goes with standard C++ library. You just need to get used to it. But in terms of using this, it is actually like more or less straightforward. And functional programming encourages this pipeline way of programming. You get some data, you pipe it to some transformation pipeline, and then you pipe it to another transformation pipeline. And basically, all our programs are just glorified transformation pipelines. And let's do exactly that. How we can double every second digit with like this transformation pipeline. So here we are not going to have like interleaving boolean. We will actually now go back to our initial idea of having like number 0, 1, 2, 3, 4, or like 1, 2, 3, 4, 5, and we're actually going to check whether the number is even or not. So in C++, like in these ranges, you can actually generate an infinite sequence of numbers starting from a particular number. I think it's called iota. So this thing here, just like this little guy, it generates an infinite sequence of numbers starting from the specified number. Obviously, there are different overloads, like you can start from one number to some other number. And I say it's like infinite number. You may ask, how do you store like the infinite number of numbers? The idea is that they're generated lazily. They're not generated unless you consume them. So it's like sequence lazily. It doesn't even store all of those numbers. It just generates you the next number one by one. So we will get these numbers. And now we have like digits, and we have indices, and what we want, let's say our digits 4, 4, 3, 5, whatever, and we have sequence of numbers 1, 2, 3, 4. So we kind of want them to pair together. We have sequence of digits and we have sequence of indices, and I want to know which number is even. So there is another thing here which is called, that we use zip, and zip basically takes two sequences and returns you one sequence with like pairs of elements. So we can say that I have two sequences. First of all is infinite sequence of numbers starting from 1, no big deal. A second is our digits. So I can actually like have digits as one of the parts. Maybe not, but we'll see what we can do here. So we have this zip like pairs, and now we want to actually transform all of these things. So let's actually do double digits. This is going to be our view, and if you want to like, so this view, it kind of generates pipeline, and as we've seen in the form, you can pipe it to another stuff. So this zip gets us kind of sequence. You can like think of it as a stream. It gives us a stream of pairs, and we wanted to pipe it to another stream, and this one is called transform. I don't know why they chose a like long name. Usually it's called like map. In most functional languages, like really short map. But the idea is that now we want to map elements of this like sequence. So we have pairs, and we are going to use lambdas here. So lambda is like an anonymous function. I'm not going to create a separate function and name it. I'm going to create just like a simple lambda function, and someone says it sounds exactly like Python, and it is. So Python has a lot of these functional features. Python has lambdas as well. You can iterate for this stuff, and maybe for this particular problem, maybe a bit overkill. I'm just trying to show how to do this in a functional way. But all of these functional features are actually present in all mainstream languages: JavaScript, Python, C++, Java, which is why it's actually a good thing to learn. Like if you learn it, it's a transferable knowledge. You can go to another language and you know this concept. Like even though I've been writing like Haskell and OCaml, I know this like functional stuff, like maps, filters, whatever stuff. I can just go to C++ and I can learn the syntax, like this pipey way, this standard libraries, and then I can reuse this thing. So it's good. Well, but you still have to learn how to do it in your particular language. Anyway, we have this like lambda, so we're taking a pair. I'm just going to let the type inference do its job and say that it's just some pair. So like auto means like infer some type whatever, and here I'm actually going to destruct this pair. So like this is like index and digit is pair. So this is like one also of the new C++ features. Like if you have some special structures like tuples or pairs, hey, hello. If you like tuples or structures, if they provide nice API, then you can kind of destructure them in elements. And because pair has two parts, then we can destruction into elements, and it will be copies. There are some rules how you can do this, but basically we want to transform this thing kind of like, if it's like index is even, then we want to double the digits. So we are going to return a new digits, and we're going to use ternary operator here. Let's say if it's even, we're not going to use a JavaScript library is even to check the number is even. Sorry to disappoint you, but we're going to do it like good old stuff. Number is even, then we want to double. We return not by 2, what I'm saying, by 2. Otherwise we just return the number. So here we kind of like doubled every second digit. It does complain about this stuff, so this should comply. The worst thing I expect is that oh, obviously it's a typo. I need to use car digits. Digits is a function. Okay, now it does compile. Well, sometimes it happens. You see a really long error, but all you did is just a typo. Happens to everyone. So the good thing here, does it? Maybe I need to configure my VS Code properly to like have proper type inference. But if you hover over like things like zip or transform, it tells you the view of this stuff, which is not always readable. But here kind of what we did, double digits. So if you compare this implementation to the previous one, to commented one, you can say this is like less readable in a sense that this is like simple for loop, you can understand it. There are some benefits here, like you cannot easily like take out of bounds. Like you already provided an element of this like structure, so you don't access it by index. You cannot have like index out of bounds errors and stuff like that. There are some benefits. It's more like on this toy example and simple problem, we're trying to see these approaches. So we have double digits. Let's actually print them just to make sure we like we didn't do anything stupid. Let's do some printing. So we do digits, we do for int, does it return vector event? Anyway, digits and card digits. Why does, okay, semicolon. Print digit, print 2, and we do this again, and we print double digit, just to debug ourselves. And the good thing about this pipeline, so we kind of created this pipeline, but we haven't actually done anything. So here, when we created this object, it actually doesn't go like through the sequence. It doesn't try to map up that elements. It just creates like a virtual pipeline, if it makes sense. It just describes how the data will be transformed if you actually try to transform it, if you actually try to evaluate and go through it. So when we are iterating through this pipeline now, so instead of doing card digits, we are doing double digits. So this is the place where we are actually forcing this pipeline to evaluate, to do the stuff. But when it's created, it just no op. It doesn't do anything. Let's see. Okay, I need to actually run this function, not just okay, we don't need digits anymore. Do validate 2. Let's run on a big number immediately. Okay, so we see digits, and we see so this is in reverse order. This is like numbers, they're reverse order, and every second is doubled. So looks like it does the stuff what we wanted to do. So the next step in our pipeline is that we now actually want like to have double digits to single digits. So we have this like sequence. Some of them are digits, some of them are double digits. So here we can do, like in this for loop where we iterate our pipeline, we can do something similar like we did before. Like we check if it's digit bigger than 0, then we take both digits and we add them to sum. So this could work. But remember what our goal was. Our goal was to build this kind of like small reusable like components that we can reuse. So we have this function digits. Ideally we want to reuse it. We don't want to repeat our digits or whatever we do, and we want to transform like our sequence to digits. So actually if you think about it, we have a like a sequence of numbers, and we want to transform every number to kind of like to list of digits. So let's say if we actually have this, let me take this example. If I have this sequence, I kind of want to transform it to this, if it makes sense. I kind of want to split all of these like numbers into digits, and then I will have like single stream of all of these things. So we actually have a function that does digits. If we apply it to one number, we will get this one number. If we apply it to number of 2 digits, we will get all of these 2 digits. So let's actually transform every number to digit. So I do hope it will work. So let's see. So actually what we can do transform, and see on the previous step we have kind of like we had a pair. So we had like a pair of index and digit, but we return only just digits. So we moved from like digits to pairs, then we transform it back to digits. Now here we have just a digit, and we can actually say that it's again in digit. We know what's the type, and I want to kind of, so it's like this is digit, but it actually can be more than digit. So let's call it like double digit, just to have less confusion. And here actually I can return just digits of this double digit. So I don't need to implement anything. I just have like this function that already does the digits. Here it doesn't work. Now digit is no longer digit because now we had the pipeline, had a view that generated numbers. Now it's a pipeline that generates vectors. Like we transformed every single digit to like a vector of digit, whatever matters. But now we kind of want to flatten. So if you go back to our example, we had this, we want this, but our current step is this. So we have one sequence of 1, we have sequence of 1, 6, we have sequence of 8, and we have sequence of 2. So we kind of produce all of the stuff. So what we want to do, we want to kind of flatten this collection. So the question is digits built in? Digits is not built in. This is a function we implemented. So sometimes you do have to solve problems on your own. You cannot rely everything on always on just a standard library. Digits is what we built. So again, I hope it works, but there is a standard view that called join, and it actually kind of well, it does what it does. It does this concatenation. You have a sequence of something appendable, some collections. In our case, it's a vector, and then we can just join them, and we will get a single of all digits. And if you try to run it, I did not expect this to work at all, but surprisingly it does. So you see, when we did this stuff, we doubled 8, it became 16, but now we kind of converted 16 to 6 and 1. So we have now the sequence of all singular digits. So this is our pipe. This is kind of how we transform data over and over again to apply, and we reuse digits several times, so we were able to reuse this function, which is nice. And now we have this pipeline, and we don't want to print digits. We actually want to consume we want to consume them not by printing, but actually by summing all of those digits. And you'll be surprised, there is a standard function to actually find the sum of all digits. And it's in the ranges library, but now it's not a view. So view is, you see, we kind of create this pipeline, how the data will be transformed. But now we want to aggregate, and you have multiple aggregations. You can you can combine the results back into vector, you can print them like iterator, or we want to aggregate them. And what our aggregation is that we want to sum all of the elements, and there is this function in ranges which is called fold left. Let me check. I think it's actually not in the ranges library, it's in the algorithm. This is one thing I find a little bit annoying. So some of these libraries, even though it says std ranges fold left, it's actually in the header algorithm. So we need to include one more header here to actually use it. Let's see if it, okay. So fold left is kind of like this function. Actually, let's go back to the browser. It explains. So you give it like a range. Let's look at this last line here. It's what we are going to use. You give it a range. A range is here. You give some initial value, and you give a binary function f. And what it does, it like explained here, it applies function f to the initial value and to like the first element, then you get the result and you apply it again to the result of that and to the second value, and then so forth. So it's kind of folds your sequence from the left, but basically just applies the same function over and over again. And if you think about it, if you think about what we did in the previous digit implementation, this is what we did. We kind of have like a sequence of numbers, and we apply the sum operation to our sum and to the next digit. So we do over and over again this like plus operation. So we need to specify a range. Our range is let's call it double digits. We need to specify initial value. So we want to find the sum, and initial value for sum is 0. Like if you add 0 to all numbers, like it doesn't change the result. And now we need to specify binary function. So in functional programming languages, you can use the operator plus like directly. You can just say that plus is a function. In C++, like operators are not functions directly. You need some kind of like functional object that can actually do this stuff. And for plus, there is actually already a standard object called plus. So can we go to it? I think it's in the utility. But this is like okay, let me show it. I think it's in the description as well. There are some examples, so it's here. So plus is like this really simple object, which is like not much to tell. It just has one operator around brackets, and it applies to two values, and it just returns the sum of all values. So it's like a really simple struct with nothing stored inside it, just to simulate this kind of like function. This is how C++ does functional programming. And by the way, if you want to write your own functional programming language, like compiler, and you want to have lambdas and closures, probably you have to do something like that internally to simulate like nice closures. Anyway, so now we have like sum, and we do the same. Sum modulus 10 equals 0, then we validate it. And now we can uncomment, and let's remove also all of this debug printing. It doesn't matter. It is not really entirely true. And I'll remove this comment just so we can compare functions. And let's actually run and see if it compiles. Yeah, all tests are passing. This is validate 2, and this is our validate 1. So you can see in terms of code, it's actually not really bigger. If you consider functions digits together, then yeah, there may be this, but this like 8 to 27, what, like 20 lines of code, and this function is 19, maybe like 18, so not really much bigger. But we were able to reuse digits. You can reuse it later. You have this like overhead, and it's definitely harder to read if you never seen this, like what is going on, what is happening here. But again, it's like a small problem, and the benefits start really shine when you really reuse all of the stuff. So you see here we implemented digits once, and we already reused it twice. Imagine you have to reuse it multiple times. And this functional ranges, it kind of catches this like popular patterns that what you need to transform every element of the sequence. You need to maybe filter, and you want to keep only some elements of the sequence. Again, you join some zips, and there are lots of like dropping and taking, all of this stuff, and then finally you aggregate all of these things. So it's kind of like the idea of how to transform, and in real life maybe like for something like Luhn algorithm for finding digits, it might be overkill. It's more like a testing exercise. But in real world, you do work a lot with collections. Let's say you have a list of users and you want to filter them by age, and you want to transform, you may apply some transformation, you want to run multiple requests, maybe even in parallel do the stuff. You do a lot of transformations with real world data. When I was writing a camel at my job, this was like a lot. And pipelining data, lists of data through like pipeline of functions is actually what the job looks like. You just transform all of the data, and this is how you do it even in C++. You just don't do it like you don't do it explicitly with pipelines. You more like rely on implicit pipelines. Like here you have like loops and they transform data, they do it in place, and you do like all of these things. And again, this function is definitely less performant than our previous one. It does allocations, but if you can write it quickly, if you can compose all of this stuff easily, because what you can do, you can actually like extract parts of these pipelines into separate functions and reuse them. Like you can actually have a function that converts numbers to digits. Let me actually show you. There are some questions. Probably also takes lambdas. No, I think if you're talking about here, yes, I think you can pass lambda here. I don't see why not. Yeah, I mentioned about views transform and views map. It's not really a good idea. Will this be available on YouTube? Yes, I do hope to upload it on YouTube. I haven't turned on any music, hopefully no copyright strikes unless anything else, but yeah, let me show you just one thing. Let's say you want to have a function that takes like sequence of numbers and it just transforms every number into like digits, and then it provides you a flattened list of digits. You can actually just take it and extract this, and this is what like the power of functional programming that I like, that you can just copy almost arbitrary piece of code, you can extract it, and then hey, you can use it. You cannot always do this like in imperative programming languages. So let's call the function flatten digits, and this function will return our pipeline. So and I can just delete this, insert here, say return. Hey, let me format it a little bit nicely. Okay, not the nicest formatting, but you get the idea. And here I can just say flatten digits. So I don't okay, it's a function call. It actually needs to create. So I can now reuse. If I have another list of numbers, let's say 1 2 3 4 5 6 7 8, I can just pass it to this pipeline of functions. Like I can easily reuse this. And if I need to extract, I mean, all of the steps I can easily be extracted. It's not easy to extract in this function, and but you can reuse. And this is kind of like the trade-off here. If you write this highly specialized implementation, it will be faster if you really need to squeeze a bit of performance, but it's kind of like monolithic. Everything is too tightly coupled and you cannot easily extract it. This, not as fast, it's not as bad. I mean, if people write Python, Ruby, whatever, and it works good enough for them, it definitely won't be slower than this. But you have this benefit of being like able to reuse all of this stuff. Like if you ever need to extract all of these pipelines of transformations and combine them in an arbitrary way, it becomes almost like a playground, and it is fun. Some people can say it's not really productive, but I think the fact that you can just like copy paste, create function, and then reuse it again, it is really productive. Like it's really powerful. You can just do this stuff. So yeah, that was the first homework from this Haskell course. So there is actually like another task which is Towers of Hanoi. I'm not going to solve this. If you like me, if you ever try to solve this problem, you probably have like some flashbacks about this problem. How is this? popular meme with this. It's like it's really insane. It is really easy to implement. Like basically this is like the entire algorithm implementation, and if you follow it, it's really easy. Just some recursion. It might not be really easy to understand why it works. It might require some little bit gymnastics, and it's an interesting exercise in recursion, but there is no really anything specific and like functional programming or Haskell to do this. Maybe one day we will fight all of these flashbacks and all of this stuff, but for now let's keep this part and let's keep it light. There are some questions in the chat. I'll try to answer them. How do you approach error handling in C++ exceptions, errors values with enums, or the newest the exceptional? I think it's called expected. Yeah. So there are different ways. I always prefer errors as values, even at work. We follow errors as values. I was really surprised. I went into this heavy C++ shop, but apparently errors as values is the way to go. People tell me don't throw exceptions, we prefer errors as values. Errors as values might mean different things. Sometimes it means you just return int code, and they're unique int codes, and you just search for them to figure out what they mean. When you want to return some payload, you usually pass a mutable reference as an argument, and it returns your payload. You can return state variant or whatever stuff. I haven't really explored this in Anger. I want to do state expected and all of this stuff. The problems usually come when you want to have composable errors. I have 3 errors from this parsing module, and I have 3 errors from this HTTP client module, and I have combined into this new wonderful data type of 6 possible error cases, and it's not really easily achievable in C++. So there are maybe different versions to be used, but yeah, definitely I would discourage using exceptions. I think they usually make it really hard to think. You can always get away with errors as values, because I've been using functional programming for a lot, and errors as values works, not always ergonomic. I mean, even in Go, if in Go they can duplicate this if error not equals to nil and get productive, get a lot of stuff done, then I mean, it is errors as values. It's just not the best way, not how I would do it, but it is errors as values, and it works. So definitely, I recommend errors as values. And yeah, I think that's all for today. Let's keep it light. I'm not sure how light it was. We started with this simple function introduction course to C++, and we immediately jumped to ranges and all of this stuff. This fold left function is from C++ 23, so they implemented a lot of these ranges in C++ 20, but they did more in C++ 23, and they're going to do even more in C++ 26. So fold left is this stuff. And yeah, the plan is to just go through this course. There are lots of homeworks. As you can see, let's go back. There are some algebraic data types. This will be fun. The next one, it's immediately there's some recursion, hierarchy function, lazy evaluation, monoids. I think this will be a really interesting one, and obviously functors, applicatives, and monads. So we are going to look into monads. And if you've seen my post on Twitter about monads, yep, we are going to do that. We're going to look into that in detail. So stay tuned. Maybe I will be able to stream tomorrow as well, so tune in, but at least I'll try to do once per week, maybe before Advent of Code. We can finish all of the series and see how it goes. Anyway, thanks for joining. I think that's all for today. Who is this video series aimed at? Great question. This video series is aimed at people who are interested in this video series, particularly people who maybe want to learn more C++, they want to maybe see how functional programming works in C++, maybe they want to have some fun, maybe they just want to see how a senior software engineer from Bloomberg struggles to write even the simplest function. Pretty diverse audience, I would say, but definitely if you find it interesting, at least from this session, this is pretty much what to expect for all of the next series. It will be pretty much like that, but different problems and more into C++ and all of these goodies. And you have to kind of use modern functional features, modern C++ features to solve all of this stuff. So we are going to look into modern C++ features. Anyway, yeah. Thanks for joining, and see you, I guess, next time.